Good afternoon, students. In this chapter, we will discuss and study first order circuits. First order circuits are circuits described by first order differential equation. We have RC circuit where there is a resistor and capacitor, and RL circuit where there is a resistor and inductor in series. And we have RLC circuit, which is the second order differential equation, which we will study in the next chapter. So in this chapter we study source-free RLC circuit, source-free RL circuit, unit step function, the step response of RLC circuit, and step response of RL circuit. Now, to start with, we start with the RLC circuit. If you see, this is a simple RLC circuit. We have a capacitor and a resistor in series. Now, the capacitor may be initially charged. So, it will discharge through the resistor. If the capacitor stores an initial energy, then it will discharge through the resistor. In order to formulate the first order differential equation, let's apply KCL. For example, KCL at this node, IR, the current through the resistor, plus IC is equal to 0. But we know IR is V over R, and IC CdV by dt is equal to 0. Then if we rearrange this, we have the integration of dV over V and the integration of dt times -1 over RC here. We know the integration of dV over V is ln, and then we evaluate from t equal to 0 until t. Right side we get minus t over RC, and this will be ln Vt over V0. Of course, ln is to the base E. Then if we rearrange, we get the voltage across the capacitor, or the voltage across the resistor is the initial voltage times e raised to minus t over RC. We call this the transient response of the capacitor because there is no source. It is source-free response. If we see this equation, it's an exponentially decaying function, and with initial voltage V0. The term tau, it is called R times C. Tau is equal to R times C is called the time constant. So again, if I go back here, when t at t equal to 0, we have V naught, the initial voltage, and then when t goes to infinity, it will decay to 0, which will give us this diagram. As you see, this is the capacitor voltage versus time. It starts from V naught and it decays. Where at t is equal to tau, the capacitor voltage becomes 36.8% of the initial voltage. Now, another characteristics of this RC circuit is what will happen if we vary the time constant, which is R times C. If you see these curves, we have the first curve R times C 0.5, R times C is equal to 1, 2. As we increase the time constant, then the capacitor voltage will decay slowly, or in other words, when the time constant is smaller, then the capacitor is discharging more quickly. Actually, it is also the same as when it is charging, that we will see in the step response. The capacitor voltage with time, if we see after 5 time constants, it will become just less than 1% of the initial voltage, which means actually the capacitor voltage is almost discharged after 5 time constants. The current through the circuit is, for example, the current through the resistor is the voltage divided by the resistance, which is given by this formula, and the power is the voltage times the current, which is given by this formula, And if we try to find the energy absorbed by the resistor, it will be given by this equation. The integral of the power will give me the energy. And if we integrate this, okay, we have 1 over 2c v naught square 1 minus e to the power of minus 2 times t over tau. Now, if we see this equation, the energy of the resistor, the energy absorbed by the resistor at t equal to 0, at t equal to 0, this is 1, 1 minus 1 is 0, Of course, initially, only the capacitor has energy, but when t goes to infinity, the total energy which was in the capacitor will be absorbed by the resistor. As t goes to infinity, the energy will become 1 over 2 times c times v naught square. Now, how to solve RC circuit? If we have RC circuit, how to solve the RC circuit? That means how we find the voltage with respect to time or the current with respect to time. Okay, so steps to solve the RC circuit. First, we need to know the initial voltage of the capacitor, which is V naught, and we will convert the circuit to one resistor and one capacitor, one equivalent resistor and one capacitor. The equivalent resistor is the Thevenin resistance, actually. Then we will apply the equation that we saw earlier, okay? And when we calculate the time constant, tau will be R times C. R will be now R Thevenin times C, okay? Now we have this example. For example, this is one example. This is an RC circuit. We have resistor, this resistor and this capacitor. And the initial voltage across the capacitor is 15 volt. And what is the voltage across the capacitor with time? Okay, this is the required. This is required from the problem. First, we consider the capacitor as a load. When we consider this capacitor as a load, with the rest of the circuit, and the rest, we will find the equivalent resistance of the rest of the circuit. If we see the rest of the circuit, considering the capacitor as a load, we have 8 ohm in series with 12 ohm, and then in parallel with 5 ohm. So 12 plus 8 in parallel with 5, which is equal to 4. So the equivalent resistance, or the Thevenin equivalent resistance, will become 4 ohm. Then the time constant is 4 times 0.1, which is 0.4 second, and then we just use the equation. The capacitor voltage is equal to V naught e to the power of minus t over tau. And we have this equation. What is the voltage across the 12 ohm resistor? The voltage across the 12 ohm resistor, we can find it by voltage division, which is V of x is equal to V, the capacitor voltage, times 12 over 12 plus 8, which is given by this relation. And of course, the current through the 12 ohm resistor is Vx over 12. You can do this practice exercise during this your class time, and also after your class time you can do this also. The second example is another example. The switch in the circuit below is opened at t is equal to 0. Find the capacitor voltage for t greater than or equal to 0. Okay, that means we need to assume before the switch is opened, the capacitor reached steady state. Steady state means we know that from chapter 6, when the capacitor reaches a steady state, then it will be opened. It will be open circuit, and an inductor will be short circuit. So that will be our initial voltage of the capacitor. Then when the switch is open, then we have that initial voltage of this capacitor. Of course, we have the equivalent resistance 12 ohm with 4 ohm. Okay, so how we find the initial voltage? Simply because the capacitor is open here, then we can say 12 ohm is in parallel with 4 ohm, and we can find this resistance. And by voltage division, the capacitor voltage at 0 equals 12 in parallel with 4, 12 in parallel with 4 plus 6 times 24, which is 8 volt. After the switch is open, the equivalent resistance is 12 in parallel with 4 ohm, which is equal to 3 ohm. And the time constant tau is R equivalent times C, that is 3 over 6, 1 over 2. And then we replace it and we find the voltage across the capacitor. The energy stored in the capacitor is 1 over 2 CVC0 squared. This is the energy at time t equal to 0. Just it's a matter of putting the numbers and calculating the energy. Source-free RL circuit. Like the source-free RC circuit, we have the source-free RL circuit with an inductor and a resistor. This is also described by first-order differential equation. For example, this is the current. Using KVL, we have VL plus VR is equal to 0. What is VL? L di by dt plus IR is equal to 0. Then we rearrange di over I, this minus R over L, integration of dt is t, then integration of di over I is ln, and then we have ln of I at time t minus ln of I at 0 is equal to negative R over L times t, and after rearranging I at time t is I at 0, the initial inductor current, e to the power of minus R over L times t. So we have time constant also for the RL circuit. The time constant for the RL circuit is L over R. Okay, L over R. So the inductor current with time is I naught e to the power of minus t over tau. And at equal to 0, we have the initial current, and again it will decay through time, exponentially decaying. And at t is equal to tau, we have 36.8% of the initial voltage. And we have the time constant L over R. And the voltage across the resistor is I times R, which is like this. And then the power absorbed by or dissipated by the resistor is VR times I, given by this. And then we can calculate the energy absorbed by the resistor through time is given by this. And after calculations, we'll get this. If we see again this equation, at t equal to 0, the energy absorbed by the resistor is 0, because initially the source is only the inductor. But at t equals to infinity, e to the power of minus infinity is 0, 1 minus 0 is 1. Then the total initial energy which was available in the inductor will be dissipated or absorbed by the resistor, which is equal to 1 over 2 L I naught square. If we try to compare the RC and RL circuit, similar, the equation is similar. What's the difference? Okay, in the case of the RL circuit, we have the current through the inductor I naught e to the power of minus t over tau, and tau is L over R, and the voltage in the case of RC circuit, V naught e raised to minus t over tau, where tau is RC, and a similar decaying function, except this is current and this is voltage through against time. Now, how we solve source-free RL circuit? The same, similar to the RC circuit. We need to find the initial current across the inductor. We need to find the time constant, and then the Thevenin equivalent resistance. And from the Thevenin equivalent resistance, we calculate the time constant tau L over R equivalent, or R Thevenin. This is an example of RL circuit. For example, initially the inductor current is 10 ampere. Calculate the current at time t, and I X through the 2 ohm resistor. Now, if we see this circuit, how we find the Thevenin equivalent circuit? Of course, there is only dependent source here. There is no independent source. We can use a 1 volt 1 volt source test voltage, and we can calculate R Thevenin. Okay, this is a 1 volt. We remove the inductor and 1 volt test voltage, and to get the current I node, we can use nodal analysis, we can use mesh analysis, whichever convenient for us. Here I used, for example, mesh analysis. So if you see, we have two loops here, two loops. In the loop 1, 2I1 minus I2 plus 1 is equal to 0. And in loop 2, 4I2 plus 2I2 minus I1 minus 3I1 is equal to 0. Minus 3I1 is equal to 0. And I have two equations, these two unknowns. And the I1 will be minus 3, which if I1, because I1 is counterclockwise and I0 is clockwise, then I0 is minus I1 3 ampere. From this, the Thevenin equivalent resistance V0 over I0, the test voltage is 1 volt over the current is 3, and we'll have 1 over 3 ohm. And from this, we can calculate tau. Tau is L over R equivalent, which is this. Then we have this equation I naught e to the power of minus t over tau. The voltage across the inductor can be found from the derivative of the current. V is equal to L di by dt. The derivative of this will give me this. Okay. And the current through the 2 ohm resistor is the voltage across the inductor, because they are in parallel, divided by 2. We can solve the previous equation also directly without using Thevenin equivalent resistance. How we solve it? Again, we have these two loops, first loop and second loop. In this case, we don't remove the inductor, we keep it, and applying KVL in loop 1, the voltage across the inductor is half di1 by dt plus 2 I1 minus I2 is equal to 0. And we have one equation here applying KVL in loop 2, 4I2 plus 2 I2 minus I1 minus 3I1 is equal to 0, which we have this equation. And we can express I2 in terms of I1. Then we have this, and we put it in the first equation. And by putting the first equation, we get an equation where we have only I1, di1 by dt plus 2 over 3I1 is equal to 0, first order differential equation. I1 means the current I here. And if we rearrange this, di over I is minus 2 over 3 dt. And if you do the integration, and after simplification, we get I of t, I naught e to the power of minus 2 over 3 times t. You can practice with this circuit also. This is an RL circuit. Again, you need to find the Thevenin resistance, and then you have to get tau, which is L over R. This is another example. In this case, the switch in the circuit has been closed for a long time, which means the inductor reached a steady state. The inductor reached a steady state means it becomes short circuit. After that, we have the initial current of the inductor, then the switch is opened. Okay, so the initial current of the inductor is, that means the steady state current in the inductor. Okay, before the opening the switch. So before opening, this is short, and when it is short, this 5 ohm resistor, there will not be current in the 5 ohm resistor because it's shorted. So the 12 ohm and the 8 ohm resistor will be in parallel, and by current division, we can find the current through the inductor is 8 opposite resistor, 8 plus 12 times 5, which is 2 amperes. This is the initial current of the inductor. After that, the switch is opened. If the switch is open, then we have the resistors, these 3 resistors in the inductor, and we should find the Thevenin equivalent resistance. If we find the Thevenin equivalent resistance, the 12 ohm will be in series with 8 ohm, considering the inductor is as a load, and the 12 plus 8 ohm will be in parallel with 5 ohm, which will give you 4 ohm. then tau is L over R equivalent, and we calculate it like this. And then I of t is I naught e to the power of minus t over tau, and it's a simple substitution of numbers, and we have this equation. And you can practice with this problem also. This problem. With this, we finish the source-free RL and RC circuit. And I hope you understand. Please use the practice problems to further get more understanding. And if you have an issue, you can always write an email to me or ask questions using Blackboard. Thank you.